This week's SIG test is on evaluating limits algebraically, and so we want to go ahead and use the different techniques that we've learned about evaluating limits in order to make sure that we can find the limit of each of these functions. So starting with function a, notice that we have the square root. So anytime you see a square root like that, not like this over the entire thing, but just one square root either in the numerator or denominator, or even two square roots for that matter, you'll notice that when we plug in 25 into here, we get 0 over 0, which is the indeterminate form. You could use L'Hopital's rule, but if you want to do it that way, go ahead, but I don't really want to use the product rule down here, and I'm not a big fan of taking derivatives of square roots if I don't have to. So instead I'm going to multiply by the conjugate, or rationalize the numerator, as we've learned before. So I'll multiply by the square root of x plus 5 over the square root of x plus 5. And when I do that in the numerator, I'm left with x minus 25 because that's the difference of squares, and the middle terms are going to simplify. In the denominator, there's not much I can simplify, or I should say it wouldn't be worth it to simplify, so I'm just going to leave it as multiplied out. Factored out. And then you notice that by doing that, I have an x minus 25 in the numerator and denominator, and I can simplify those to 1. So now I can take the limit as x approaches 25 of 1 over x plus 1 times the square root of x plus 5. And so if I plug in 25 now, I no longer have the indeterminate form. Instead I have 1 over 25 plus 1, that's 26, times the square root of 25, which is 5, plus 5. So that's 5 plus 5 is 10. So this would be 1 over 260. For the second one, remember, anytime you see a limit as x goes to infinity, you should think of a horizontal asymptote. And so we're going to look at the degree of the numerator and the degree of the denominator. And because both of these are underneath a square root, that means that both of them would be square rooted. So x squared would be technically to the first power, and down here x squared will also be technically to the first power. And so as we look at them, because they're both underneath square roots and they're both the same degree, then we're going to look at the ratio of the leading coefficients. So something you have to take into consideration is the fact that the entire expression is under a square root. So when we look at the ratio of the leading coefficients, we're looking at the square root of it. So the square root of 9 would be 3, plus or minus 3, but we'll talk about that. And then 4, the square root would be 2. So because we're going to positive infinity, it's going to be positive 3 over positive 2. There's not much work to show for that one. That's just a conceptual question. For this one, excuse me, we're approaching 1 from the negative side. And so remember, when we plug in 1, we get 0 on the denominator, which is not okay. And we don't have the indeterminate form, so it's not like we can take the derivative of the top and bottom separately like we did with L'Hopital's rule. So instead, what I'm going to do is I'm going to evaluate numerically by plugging in numbers that are really, really close to 1 from the negative side. So coming from the negative side, those are numbers less than 1. So if I can think of a number less than 1, like 0.999, if I plug in 0.999, because 0.999 is really close to 1 from the left-hand side, I would get 1 over 0.999 minus 1. And on the denominator, again, this is more of a conceptual question, but in the denominator, as you think of 0.999 minus 1, that's going to be a really, really small number, like close to 0, but it's going to be negative, because 1 is bigger than 0.9999. So this is going to be a negative number really close to 0. And remember that anytime you're dividing by, and I'll just put this notation, I know that's not exactly right, but just to keep track of what we're talking about. If you have a negative number that's really, really close to 0, anytime you're dividing by a number close to 0, then the limit is going to infinity, or that number, I should say, is going to infinity. It's getting really, really big. And so in this case, it's going to negative infinity, since this is a negative. And so if you read the directions, it says, note if the limit does not exist, write does not exist, but also say if it is approaching positive or negative infinity. So for the answer for this one, we're going to write that it does not exist as a limit, but also that it's approaching negative infinity. And so that's why we know that the limit does not exist. And then for this last one, you can use the factor and cancel method, because again, if you plug in 2 in the numerator and denominator, you're going to get 0 over 0, which is the indeterminate form. You could use L'Hopital's rule and take the derivative of the top and bottom if you wanted to, but for me, factoring is just as easy as L'Hopital's rule, so I'll show you by well, I guess I could show you both ways. We have x plus 2 times x minus 2 over x plus 3 times x minus 2. So notice that we have this x minus 2 factor that will create a hole for us. So now we have x plus 2 over x plus 3. And if I plug in 2 now, I get 2 plus 2, that's 4, over 2 plus 3, that's 5. And then alternatively, I'll write it in red. If you were going to use L'Hopital's rule for this, you could take the derivative of the numerator, that would be 2x, and the derivative of the denominator, that would be 2x plus 1. And then you could plug in the 2 into that as well. So if you plug in 2 into that, you get 2 times 2, that's 4, over 2 times 2 plus 1, that's 5. So using L'Hopital's rule, I'll just abbreviate, you could also have found the derivative equaling 4/5 that way. So up to you about which method you use, but these are the different strategies we've looked at to evaluate limits algebraically.